Okay,
Yes.
you can see the notes here. Okay, so our next speaker is Jeffrey Pan from Bronco AI Incorporated. He's going to talk about AI agents for DV Debug, which is obviously a big topic. I think it's still estimated 30 to 35% of project time. Jeffrey Pan is the co-founder and CTO of Bronco AI. Before starting Bronco, he pioneered award-winning techniques in efficient ML and the hardware, software co-design at MIT and scaled foundation models used by hundreds of millions at top industry lab. Jeffrey, thank you.
All right. Hello, everyone. Jeffrey here from Bronco. Obviously, there's been a lot that folks have talked about AI agents today. Pretty much what I'm going to go ahead and do is I'm going to go preach to the choir a little bit. I'm going to go give a little peek under the hood on how we've come to AI agents, how they're very different from the types of machine learning algorithms that you might have been familiar with in the past. And then I'll go and share some of the experiences that we've had going and deploying and actually using these models in production, finding real bugs on live regressions at some of our customers. So with that, as most people know, I'm talking to a verification audience here. Verification is the biggest bottleneck now in the chip design process. Anywhere from, the studies vary, but anywhere from 40, 50, to 70% of the actual design timeline is now spent on verification. And this is really only going to get worse for a couple of reasons. Firstly, we're just seeing generally shorter timelines as ASICs have gone and continue to explode in popularity, especially with this recent massive demand in compute for AI models. We're just seeing timelines get shorter and shorter for new silicon. Second is just designs are constantly getting more and more complex, right? As your design complexity is increasing, that potential verification space that you have to go and actually search through just gets exponentially worse. And then finally, verification teams aren't getting much larger. There's fundamentally, with how much the demand for verification has grown, simply kind of the old method of really just kind of like scaling up existing practices or your existing team is just really not going to keep up in this fast-paced environment. So folks have been thinking about bringing in ML and AI-based solutions into verification for a while now. And something I wanted to call folks' attention to is just how this fundamentally adds value in a very orthogonal way from how a human team normally would. When you're on a verification team, or if you take a individual DV, they might be a generally smart human, but unfortunately, generally smart humans typically are really only good at focusing on a handful of tasks at a time. And what that ends up in is if I go and look at the just scale of the verification and that needle in a haystack problem that you have to go and solve. Really what we want to do is we want to be putting human effort where there's actually very high ROI, right? We want people going and solving the complex corner cases. We want people thinking about coverage. We want people thinking about these complex subsystem and system level integration tests. What we don't want is we don't want your DV team to just sit there drowning under tens, if not hundreds, of daily new failures coming from some regression system that constantly have to be triaged, managed, and fought. And that is precisely where AI has a unique advantage. Fundamentally, if I have the ability to go and scale some AI model that can do that first half of debug, that means that I'm placing my people where there's high leverage, and I'm ultimately reducing that amount of that fire hose worth of work that's coming their way. However, a lot of traditional ML techniques have fallen flat in the verification and hardware space, and there's a couple good reasons for that. The first is just the traditional model of ML was very, very training and fine-tuned oriented. So, if I wanted to go and get some ML algorithm to work well on my project, I'd first go, I would collect a bunch of data about, my design, past bugs, all these things. I'd have to go fine-tune my model 6 months down the line. Hopefully I have a model that works, but oh no, all of a sudden I now have a design revision. I'm moving on to a new project. Maybe I'm bringing up a completely new different IP that I have to integrate. And all this time, I'm spending a lot of time on these human resources that I don't have to go and label and collect this data. And ultimately, my projects are moving too quickly for these models to really keep up and be useful. So putting on my old ML researcher hat here, essentially, if you look at a lot of domains where you've been able to have actually really great foundation models, this was also the case in a lot of other domains before. So for instance, back when I first started doing ML research back in 2017, the state of the art in text models was you'd have to go and fine tune a model for, again, every single task that you wanted to do. If you wanted to translate English to Spanish, you'd have to go collect a bunch of data, label it, train it. And that model obviously wouldn't be any good for summarization. Or if I wanted to go and do sentiment analysis, I would have to go collect a bunch of data, train on it, and I end up with these very, very brittle models that are really only good at one task that ends up, quite frankly, expiring pretty quickly. So how did we go from these 1,000 different models for each specific task to something like ChatGPT, where I can ask it really anything that I want to do with text? I can ask it to write an essay. I can ask it to write code. I can ask it to translate. And all those things work well. The intuition was that led us from these sort of simple models that you had to constantly fine tune to these actual generative or foundational models is basically defining a couple of things. Really, it's about finding a task that's really easy to verify. It's easy to collect data, and it's a building block for everything that you want to do downstream. So in the example in language, the real breakthrough was some researchers found that it turns out that what you can do is you can just drop out random words from a paragraph or a sentence, have some model go and essentially try to fill in the missing words. And if you do that, you don't have to spend a lot of expensive human effort going and collecting labels or manually doing translation. It turns out that just through this process of guessing what the missing word is, these models learn the fundamental building blocks of language. They learn how nouns and adjectives and verbs come together. So then if you have this really good foundational understanding of language, it actually then becomes really easy for you to go and go from generating an essay over here to going and doing translation over here. So this is all great and all, but what does this mean for verification, right? What this means is if there's some way for us to essentially, almost get down to the essence of what are the building blocks of really understanding, hardware design, verifying that said hardware design, and using these, foundational tools to go and execute these tasks, we can actually build a system that won't, because it isn't just memorizing, the details of a specific design, is actually learned just as a human would those more broader patterns of debug. We can actually build solutions that generalize well. And from a lot of these recent frontier labs like OpenAI and Anthropic, as well as in the open source, we've seen effort in that direction. We've seen effort in these reasoning models that are able to spend much more time thinking step by step through how to attack a complex problem. And we've also seen these agentic systems where models have learned how to use these tools very well. And thus, rather than this model having to, memorize, for instance, how to do math, the model just has to know how to use a calculator. So where does this all lead us? This leads us to this understanding that agents can really generalize where models can't, right? Because rather than having to go and collect a bunch of data on, and memorize that, for my design, it consists of these IPs that have these wires, oriented in this way. I instead can learn these more meta patterns on, these are the issues that I'd face when I'm verifying a network on chip versus accelerator versus memory subsystem. And just as kind of like good experienced human DVs learn those patterns where, like for instance, I'm going to be thinking a lot more about the control path for a CPU, whereas I might be more concerned about throughput and performance on an accelerator. We've been able to take these models, and by focusing on the model's ability to use tools and really think at that higher level, we're able to actually build solutions that generalize much, much better. So what that means is we can take these off-the-shelf models that know how to write code, are generally smart problem solvers, but may not know the intricacies of your design. And by fusing them with this really rich ability to understand the design, understand common industry protocols like AXI and AMBA and so on, we can build these really generalizable debug systems. So what we've gone and done at Bronco is we've built this platform for the automating these end-to-end DV flows. So we start with the verification plan, basically going through having these agents that can go through your design, read your spec, read your simulation environment, look at your design, and from that, and sort of that general good problem solving intuition, essentially back out that, for instance, for this type of design, and these are the types of issues that I would need to be cognizant of. We bring that then into test bench bringing up UVM and other industry standard test benches in a fraction of the time that humans take. And then finally, and where we've really spent the majority of our time focused is on debug. Because like I said earlier, the ultimate thing that really makes these models perform well is getting good feedback on whether or not they're actually performing well, right? And that's something that traditionally is very hard to do in verification. It's pretty easy to go and spit out a bunch of RTL. It's much more difficult to see, whether that RTL is performant, whether that RTL actually matches the spec. That is the whole point of verification here. So what we've gone and done is invested in these agents that can distill your DV engineers' best practices, use industry standard debug tools, and then thus go from any failing simulation to what are the types of failures to investigate, what tools to use to investigate them, and then work to find until we can find a root cause or handoff ticket to a human. So, kind of peeling back the curtain here a bit, what we do is we go ahead of time and ingest all this information on the project. So that all this file, your RTL, test bench, and spec files. We take in just common failure cases, and just similar to how you would onboard a new junior DV almost. If a new junior DV were to come onto your project and ask, like what are the types of common failure signatures that you're seeing, and that junior DV might ask you, if you see this failure signature, how would you go and actually debug it? And you might go and tell them, well, I'd first go and check this CSR, and from this CSR, I know it's one of these two cases, and those are driven by like this set of wires, and then slowly and steadily, that's how you go and actually back through that logic code, and then ultimately do that root cause. So similarly, what our agents do is we essentially learn that from your existing best practices, and then that becomes something that we can then go and scale across your regression. So upon any failure in your nightly regression, what we'll do is we'll assign an AI agent to that. We'll run through this debug playbook, as we like to call it, and then at the very end, we'll spit out that root cause or concrete actionable next step. And then rather than waking up in the morning to a series of new failure signatures that your team has to go and triage and root cause and debug, you wake up to root cause issues, and your human DVs are focused on the issues that really matter the most. So a couple of real world scenarios. So this is an example of next gen ASIC that we've been working with. We saw essentially a new error signature pop up on actually a regression that we hadn't worked previously on. So this was actually reasonably late into the regression. So this was an a regression that had been clean for a while. A new error had popped up at that subsystem level. So pretty much what they were like was, hey, can you go and move Bronco from this existing block level that we were testing actually up to the full subsystem? So what we did was we ingested that project context, and in about 30 minutes, we had gone through, ingested more than 200,000 lines of RTL, and just from a couple of prompts from the block owner on what the common issues were, we had kind of gotten an understanding of those common failure patterns. And then we fed in that actual UVM error. And then after 15 minutes, we read the run log and the waves. This is at that subsystem level. So these are some pretty large files that we're actually talking about here. We identified that the root cause was there was this control signal that was not propagating fast enough. 4 levels nested deep in that hierarchy. And then we pointed out that fix. It was this corner case that they didn't really hit a lot in their constrained random. And their block owner said that it probably would have taken them the better part of an afternoon, or a brand new junior DV, the better part of a week to go and get through that debug. So finally, we just wanted to spend a bit of time and talk about some of the lessons that we've learned building these systems. So the first really is rethinking a lot of these human actions. So kind of as a motivating example, I've got a waveform viewer over here. This is something that a lot of folks are familiar with, but for an AI, there's a lot of problems with this. This is fundamentally really single-threaded. I'll finish up in just 1 minute. This is fundamentally a very single-threaded interface. If you want to scale AI agents to work in parallel, we're going to have to really rethink some of the tools, and that's what we've spent a lot of time doing. Again, I mentioned we deliver most of our value through scale. Sitting at the regression, wiping out that first half of issues for a debug team. And then finally, building systems that learn and improve over time. I'll be sticking around if there's any more questions. Thanks, everyone.
Thank you.